All right, keeping going. All right, so some terminology of cardiac function. You have the cycle, stroke volume, ejection fraction, and cardiac output or cardiac output. That Q is kind of what they use for that. That's just the term that they're going to have on there. So all mechanical and electrical events occur during one heartbeat. You have diastole, which is the relaxation phase. This is when the chambers are filling with blood, lasts twice as long as systole. Systole is the contraction phase, as it contracts there. So let's say we said that earlier that there were three different phases. So the QRS complex is to the T wave. So this is the first third of, so this would actually be from here to here. My picture's a little off. It's just the best I could find. So contraction begins, the pressure rises, and the atricular valve closes. So that's the first lub that you hear when you were doing your heartbeat stuff the other day. Blood ends up going out, and at the end of it, it's the end of the systolic part. So the second part would be the T wave. So that would be 2/3 of the cardiac cycle. So that's why it says ventricular dystole is 2/3 of it here. So it's the same thing, the blue section there. So that's the relaxation phase. So the pressure drops, the valves close, and it fills 70% passively and 30% by atrial contraction. So in the end, the blood vessel is filled up, and then, or the ventricles get filled, and then it starts all over. So you could go, there's all kinds of things in here. Here's the part that, as it's going here, systole is happening, and then diastole or dystole, I don't remember how it's pronounced there. Here's how much blood is in each one, and we're going to talk about that coronary here in just a second, and here's the pressure in the atrium. So there is a formula, you may need to know this. This is a rough one. The stroke volume is the amount of blood that is pumped in one heartbeat. So it would be the end diastolic volume and the end systole volume equals the stroke volume. Generally speaking, it's going to be 100 milliliters is what the heart, depending on how big your heart is, but we're just making it nice, easy numbers here. Your end diastolic volume is 100 milliliters, and it pumps out 40, and so you're left with, or you pump out, and that what's left is 40, so you don't actually pump out all the blood out of your heart every single heartbeat. Some of it stays in there. So basically, 60 milliliters is what's pumped out approximately every single one. And you can make that into a fraction. So approximately 60% of the blood is what is pumped out of your heart every single time. So here's a nice little chart that makes it look prettier. I understand pictures better than I understand other things. So you have your beginning or the end diastolic volume at the end of dystole. It pumps out 60 to the blood vessels. What's left over is about 40% or 40 mils. So there's all the charts there. And there's a nice way of saying that with a picture. Here's what was pumped out. So here's the same two things there. So 60% is what is pumped out every single time. The total blood volume pumped per minute. So you could take the cardiac output would be the heart rate plus or times the stroke volume. So if your resting heart rate is 70 beats a minute, your stroke volume times 70 would give you exactly how much it is. So 70 beats a minute times 70, let's just say 70 milliliters, would be 4,900 milliliters or 4.9 liters per minute. Now, if that was the 60 milliliters, instead, you would take 70 beats a minute times 60, and that would be, my brain's just not working there. So your resting cardiac output would be 4.2 to 5.6, somewhere in between there. So the average total blood is approximately 5 liters per minute. So there's the other number you might need there. And let's see, there's the 70 beats per minute times 60 milliliters that we came up with a little bit ago. It's 4.2 liters. So pumping during exercise. So the functional circadian, the pumping of the heart as one unit. So you have torsional contractions, so that's increased contractions. So during systole, the heart actually twists a little bit. So that's why they're saying torsional would be twisting. So torsional So the heart twists gradually, storing energy like a spring. And the distally is where it abruptly untwists, so it twists just a little bit, and as it pumps, it untwists just a smidgen. So just kind of a cool little thing there. So when you are exercising, the biggest difference between an untrained and a trained athlete is the stroke volume. So the stronger your heart is, or in some cases, actually, the more it's stretched, because you've used it, that muscle, as it stretched, there's going to be more blood pumped every single stroke. So an untrained athlete, we said, I believe I mentioned that you have the same amount as your body needs oxygen, your heart rate, or the amount that your blood moves is going to be linear. So that's why the oxygen and blood movement is the same on all three of these. The biggest place it changes is here, where the stroke volume. A trained athlete is going to have have more blood pumped per heartbeat compared to an untrained person. So this would be like running at a treadmill at 5 miles an hour, or walking basically. And this would be the maximum that person is doing. So oddly enough, the untrained person has less stroke volume, at least in this one, at their max than the person does at a very minimal number there. And we're going to skip that one so we can keep going. So here's the other parts that I was just kind of mentioning there, is as your muscle stretches, and we do this with our muscles, the more you work them and stretch them, the stronger they get. Well, the same concept is in your heart. So the Frank-Starling mechanism is the greater muscle stretch due to blood volume. So as your actin and myosin are interacting, they can get to the point where they're actually overlapping so much that's as far as they go. And so that low stretch of the actin and myosin means they're not going to have as much contraction. Not my best slide there, apologies. But if you have it where you're using your muscle, using that heart, and it's overstretching, you're actually going to get more. That's why somebody's heart gets more stroke volume, is because they've used it and they've actually stretched the actin and myosin so that it has a higher amount of contraction per beat. And that's why someone's heart can be having a resting heart rate lower than another person's. Right, so that's the physiology behind it there. Whew. Do I get to 12:10? See if we can get through another topic here. So arteries are what carry the blood away from the heart, and then it goes to everything else. The capillaries are where everything gets exchanged. The venules collect the blood from the capillaries, and then the veins carry it all back to the heart. That was my final thing in anatomy and physiology classes. I had to trace a red blood cell through the body. So I had to remember all those things. So we have the systolic pressure. I don't have maybe. Nope, don't have them. So the systole and diastolic pressure, I had those numbers written down. I just don't have it at the moment. So the arterial pressure is 2/3 and 1/3 is where it's going to be for that mean arterial pressure. Hydrodynamics. General blood flow is required by all tissues. The pressure, the force drives it from the heart and goes out to everything else. There is what's called a pressure gradient. Am I going to get to any of that? A little bit. We're going to go to the next one. So the easiest way to change the flow is to have a gradient. So blood is going to go from the higher pressure to the lower pressure. So when it pumps out of your heart, there's a gradient of what direction it is going. The pressure gradient is what drives the flow of blood. Goes from the aorta back through the vena cava. And here's what that pressure would look like. So as it pumps, it's higher, and then it's going to get less and less and less as it gets all the way out into your muscles. And same thing, and then at the end here, it's going to come back. So it goes up a little bit as it's coming through. See, distribution of blood. What you need to know here is triple check some of these for me. Ability of local tissues constrict and dilate helps get the artery stuff back. So your blood does help carry all the things that we've talked about before, lactic acid and any of the byproducts. Just how it's all going to get returned. There's the one I wanted. At rest, here's the thing I'm pretty sure is a quiz question. 2/3 of your blood volume is in your veins. So that's why when they draw blood, they draw from a vein because that's where more of the blood is. They don't want to take it from an artery. That'd be bad. So that's the blood reservoir. That's where the lowest pressure is as it's further out. Your heart and everything has a little less than that. So 64% is in the veins. Here's just where it all is going to go. 7% in the heart, 13% in the arteries, 9% in the there, and 7% there. So that's just kind of where all the blood is in your body. These baroreceptors are what are going to help keep the blood pressure going. So if it gets too low, it's going to tell the heart to work faster. My favorite part here. So you're returning the blood to the heart. Have you guys ever seen a military graduation where somebody passes out? Or when somebody just stands in place for so long? Yep, weddings, people fall out. The one that we were always scared of in grade school was at like music festival, people on the top of the bleacher things that they had, somebody would lock their knees and then they would fall off the back with something they were always scared of. Well, there is a reason why. So there is a little valve at the bottom here that's a one-way valve. As your muscles move, it constricts and then it shoots everything back up the leg. So this is how gravity is controlling. So your muscles actually squeeze the veins as they move. And if it doesn't relax, not more blood gets in there, and that's why the person would pass out if they're standing at attention for too long, or if they lock their knees. And they also, the moment they fall down, their legs now moved, and then they wake right back up. So it's just like they black out for like just a couple of seconds. The other thing that's going to help get the blood back is your respiratory pump. So as you're breathing, it actually does a very similar thing to the blood vessels around it. And so that's another way that the blood's coming back to the heart with that low pressure. See, the blood, very quickly, I have 1 minute, transports things, keeps everything temperature right, keeps that pH balance. Here's the other fact you need to know. 5 to 6 liters in men, 4 to 5 liters of blood in women. That's just average, not perfect. The white blood has plasma in it. Anybody ever give plasma? Oh man, I did that. I got big old holes where you can see it. So plasma is 50 to 60% of your blood volume. Red blood cells do the rest of it. Hematocrit is the total percentage of each of these put together. When you spin it around, that's what it looks like when you put it in a centrifuge. You can see where the plasma is. If you ever give plasma, it actually takes it out and you can hear the thing spinning in the machine, and then they put it back in. And you can get paid for it. That's why I did it in college. How fast their blood viscosity is how thick it is. It's about twice as thick as water, and that's all I got. Boom. I can't believe I made it through that. That was probably way too fast. Make sure you